Hello, and welcome to the Advanced Response Engineering Online e-learning course video tour. What will follow are brief video segments from several training sessions to provide a glimpse of the training material for the Certified Quality Engineer training course. When you are ready to register, please first view the free course registration and operation tour.
Welcome to the Certified Quality Engineer course, which is here to prepare you to take the ASQ CQE exam or to provide you with an overview of the body of knowledge so you can apply it at the workplace and be prepared in the future to take the exam. It's a self-paced webinar offered in modules covering the various topics and subtopics that you can choose from as needed. Slides from these modules can be printed for your use during the exams. The instructors have been teaching these topics for many years within our ASQ sections and also as in-house training for multiple companies. Instructors have many years of experience in applying these concepts and methodologies at multiple employers in a variety of industries. And the instructors have actual hands-on experience working full-time in various companies and teaching these on a part-time basis. So the advantage of going through this course is that your instructors are working professionals like yourself. So quality philosophers and their leadership principles. Ones that we'll be covering is Schuhart, Crosby, Juran, Deming, Feigenbaum, Ishikawa, Taguchi, and Bill Smith. So Schuhart, he came up with the plan, do, check, act cycle and control charts, statistical process control, as you can see on there. So you can identify for processes and control and identify any out of control conditions that's attributed to special cause. Some milestones. 1924 introduced control charts, and then along with Dodge and Romig developed acceptance sampling plans, and he published the economic control of quality of manufactured products. And then 1940 to 43 Bell Labs developed most standard sampling plans for the U.S. Army, which was covered earlier on in some of the Ruckin books that you can download off the internet. So common themes of quality. Improvement's never ending. You've got to have top management commitment, knowledge, and active participation. Management is responsible for articulating the company's philosophy and goals, measurable objectives, and a strategy for change. All employees need to participate. Common language and set of procedures is necessary, and you have to have a process that's established to determine the most critical problems or causes and find solutions. So that supports the law of focus. And then changes in your culture, roles, and responsibilities may be required to achieve this. And if that's the case, then it's going to take time, along with commitment and constancy of purpose. So continuous improvement tools and concepts, such as SPC, TQM, Six Sigma, and Lean, including the theory constraints, will be covered in greater detail in other topic sessions in this course.
In our next lesson, we will cover some basics on data collection and data analysis. Statistics is a powerful set of scientific methods used to extract meaningful information from numbers. Data are collected and analyzed to draw conclusions regarding population measured and counted parameters. A population is considered the whole universe of the variable. For example, a process that makes ball bearings, where the diameter is an important performance metric, the theoretical population of ball bearing diameters would include all ball bearing diameters from every ball bearing made by that manufacturing process. Because data on an entire population rarely exists, a sample, which is basically a small subset of the population, is used to estimate the population parameters such as the mean and standard deviation. An estimate of a population parameter made from a sample is called a statistic. There are three general types of data: variable, attribute, and location data. Variable data is continuous and is measured. For example, what is the diameter of the catheter? What is the tensile strength of a rod? How long is the part? And then attribute data is discrete and is counted. Some examples are how many rejects per lot, how many defects per part, how many people bought coffee with their breakfast. Two general areas of statistics are descriptive statistics and inference statistics. Descriptive statistics are used to characterize a sample. Sample statistics include measures of central tendency, such as the sample mean, X bar, the mode, and the median. Measures of variability, such as the standard deviation, S, sample variance, S squared, and the range. And other characteristics such as the minimum and maximum of the data, and skewness and kurtosis are measures of the sample distribution. Inference statistics deals with the collection, analysis, and interpretation of numerical data using the theory of probability to draw inferences regarding population characteristics such as the mean and the standard deviation. Statistical inference can be classified into two areas. First, estimating population parameters plus confidence intervals falls into that category. And next, hypothesis testing of population parameters, where we make statistical inferences about a population parameter being equal to or greater than or less than a hypothesized parameter. And we're going to be talking a lot more about all of this shortly. Sample statistics versus population parameters. When we collect data, it is wise to plot the data and see what kind of frequency distribution we get for the data. And here we have three examples of symmetrical distributions. The first one is normal, and that's a bell-shaped curve. And you can see that it's unimodal, one mode, and that the mean, the median, and the mode are all at the center. Another example of the data may be a bimodal distribution, where we have two modes, and then the mean and the median are in the center. And then a uniform distribution, where we have no mode, and the mean and the median again are at the center. A non-symmetrical distributions where the distribution is skewed to the left. That means the tail runs out to the left side. And you can see that the mean, the median, and the mode are all in different locations. The data over here would imply that the data is highly skewed to the right. And again, the mean, the mode, and the median are in different locations. And identifying the distribution for the data is important so we know which statistical formulas to use during analysis. Two sample distribution characteristics I like to look at are skewness and kurtosis. Another very important plot is the box and whisker plot. This is another development by John Tukey. And what we have here is a box of the data. This represents the inner quartile of the data that goes from the 25 percentile of the data to the 75 percentile of the data. So this box represents the inner 50% of the data. And then from this line here, the first quartile down, represents the first 25% of the data.
Welcome to the CQE refresher course. In this session, we're going to cover topic number 2, which is the quality system. And those 18 questions are spread across 6 subtopics, being the elements of the quality system, documentation of the quality system, quality standards and other guidelines, quality audits, cost of quality, quality training. So looking at the quality system activities, you have quality and marketing. Places to look at would be the implied and stated needs of the customer, actual field performance, and customer satisfaction. And those are just some examples. Quality and specification design. So you need to be able to translate the clearly defined customer needs into technical requirements, basically, the what's into the how-tos. Manage the design process, hold design reviews to ensure customer needs are met. Quality and purchasing. You have to define the requirements, communicate them to your suppliers. You need to be qualified based on their ability to meet those requirements. And the performance is monitored and communicated with the supplier. And you have your quality of process. All right, now we're moving on to quality audits, the next major subtopic. So here in the body of knowledge, you got types of audits. So I want to be able to describe and distinguish between various types of audits, such as product, process, and management, also known as system audits. Achieve registration, such as certification, compliance, regulatory requirements, and then first, second, and third parties. Level cognitions apply. Then number 2, roles and responsibilities in audits. So you got to define those roles and responsibilities for all the participants, such as the audit team, the client, and the auditee. And level cognition on that is understand. So, all right, some parties involved in the audit. These are legal terms. You have the client, someone requesting the audit. You have the auditor, so the individual is actually conducting the audit. And you have the auditee, it's the one being audited. So look at types of quality audits now. So you have an internal quality audit. And internal is basically where the auditor is an employee of the organization. So they're on the payroll. It's also called first party audit. And that is a legal term. So all your internal quality audits are first party audits. Now external audits is basically where the auditor is an employee of the client or an independent organization, but not of the auditee. You got 2 types. You have the second party audit. So that could be yourself going out auditing a supplier. You know the supplier's payroll, and so you're auditing them. Third party audit is independent organization. It could be like a regulatory authority or a registrar. And they're free from political constraints. So remember, external audits are always second party or third party. So types of audits, there's the quality system audit.
We are at the beginning of our discussion of many important statistical tools. Before we begin our discussion on confidence intervals, I would like to review some important statistical concepts. Statistics is a powerful set of scientific tools used to extract meaningful information from numbers. In many top-performing companies, professionals use statistics to make database decisions. These are decisions that have a 95% probability of being correct, which means there's a 1 in 20 chance of being wrong, and that's considered acceptable by most professionals. If you were to take those same odds to Las Vegas, you would walk away a very rich man in a short period of time. Many of the hypothesis testing methods we're going to discuss require that the data are normally distributed or approximately normally distributed. Let's take a look at some common approaches that statistical practitioners use to determine if the data are reasonably normal. One approach is to plot the data on a frequency plot, like a histogram, and see if the data have a bell-shaped curve. Again, that approach is a little subjective. Another approach is to perform distribution fitting tests. Shapiro-Wilk, the Anderson-Darling technique, or the goodness of fit tests are three commonly used tests to fit the data to a distribution, in this case, the normal distribution. Caveat: if the sample size is small, i.e. less than 30, these tests have low statistical power and may not detect a deviation from normality when one exists. When the sample size is small, one approach I like to use is the normal probability plot. And that's this plot here on the right. And I had 10 data points, and they fall close to this line going through the center of the data. As long as the data are within what we call the fat pencil test, where you take this plot and lay a theoretical fat pencil on this line through the data, and all of the data points are within the width of that fat pencil, here shown with these two red lines. So we would look at these 10 data points and presume the data comes from a normal distribution. These same 10 data points plotted in a histogram would look like this. When the sample size is small, less than 30, sometimes the histogram, it's a little hard to...
All right, next topic. So verification and validation. So in the body of knowledge, they want you to be able to interpret the results of evaluations and tests used to verify and validate the design of products, processes, and services, such as your installation qualification, your operational qualification, and your process qualification. The level of cognition is evaluate, so that is a high level of cognition. So your verification plans should include the following factors: dimensional wear, material fatigue, process variation, variation of critical characteristics through the range of the tolerances, contamination, environmental aging, extreme environmental conditions, and these are all examples, extreme customer usage. So ISO 9001 requires that design development must be in a form that enables verifications against inputs. And designs need to be approved before release. ISO TS 6949 requires additional design outputs to define the APQP and the production part approval process. But as mentioned earlier in the course, they're not going to test you to the 6949. Test questions is going to be based more on ISO 9001. So design and development output should meet your input requirements, provide adequate information for manufacturing service, reference product acceptance criteria, specify any characteristics essential for safe and proper use. So verification is confirmation by examination and evaluation of objective evidence that a specific design specification has been met. And validation is confirmation by examination and evaluation of objective evidence that a specific intention has been met. The difference between these two activities entails who does them and the nature of your acceptance criteria. So verification and validation usually consists of design qualification, the DQ, installation qualification, IQ, operational qualification, the OQ, and performance qualification, that's PQ. Now, your design qualification may be performed by a vendor or by the user by confirming through review and testing the product meets the written acquisition specification. And if the relevant document or manuals of the product provided by vendors, then the latter three Qs need to be thoroughly performed by the users. So that's the process of the IQ, OQ, and PQ is a task of verification and validation. So let's go through the definition of those, because it is mentioned in the body of knowledge. So the installation qualification.
Let's do a short review of previously discussed statistical tools. We discussed confidence intervals for the mean using the t-test and z-test, and we discussed confidence intervals for the standard deviation and variance using the chi-square test. Because we are estimating the process mean or standard deviation from a sample, there is a degree of uncertainty. It is necessary to place confidence intervals around our estimate for the true process mean or standard deviation. Next, we discuss tolerance intervals, and this is a technique where we let the process tell us what the specification limits are, or at least a technique that tells us what the process is capable of doing. Tolerance intervals give us a region where we can expect 95 or 99% of our process output to fall within that region with, say, a 95 or 99% confidence level. A lot of companies will also calculate the tolerance intervals when they're doing process validation activity, and if the tolerance intervals fall within the upper and lower spec limits, then they deem the process capable. Then we discussed hypothesis testing, and the first category of hypothesis testing we discussed were parametric tests, where we did 1 and 2 sample means tests using the t and z distributions. Then we did process standard deviation and variance tests for 1 and 2 samples using the chi-square and f-test respectively. Regarding the process mean, we also discussed a hypothesis test for when we have 3 or more means to compare, and in that case we used ANOVA, analysis of variance, and again we used the f-test for that comparison. For the students taking the Six Sigma Black Belt refresher course, we also discussed non-parametric tests, and these are tests we use when the data don't come from a normal distribution. That is an assumption for the parametric tests to be valid, is that the data do come from a normal distribution. And when the data don't come from a normal distribution, we have alternative hypothesis tests called non-parametric tests. And in that case, we use the process median instead of the process mean that we used in the parametric tests. And we have alternatives for the 1 sample means test. It's a 1 sample median test called a 1 sample sign test. We also have an alternative for the 2 sample z-test or t-test in the non-parametric tests called a Mann-Whitney test, which is an equivalent test. And for our process standard deviation or variance, we also have alternative tests. For the 1 sample standard deviation, we can use Bonet's test, and for the 2 sample variance or standard deviation test, we can use Levine's test. Preferred is the parametric test because the next topic we're going to discuss is my favorite statistical tool. It is design of experiments, and it is the most powerful statistical tool. It utilizes both hypothesis testing and regression analysis. The goal of the DOE is to generate a mathematical model that will explain how our system works. And then we will use this model to characterize and optimize our product and process performance. So let's begin our discussion talking about knowledge and DOEs. Design of experiments is the scientific approach used by researchers to effectively and efficiently obtain the knowledge necessary for breakthrough product and process performance.